All right, so let's take a look at exercise 3. So we're going to find the local mins and maxes of the function f of x equals 12x cubed minus 9x squared. All right, local mins and maxes. So we need to find the critical numbers. Right, so we'll first find a derivative. Let's see, 36x squared minus 18x. Now this is always defined. Okay, one way you can get critical numbers of f is where f prime is undefined. That won't happen here. The other way you can get critical numbers are x values in the domain where the derivative is equal to 0. So let's set this equal to 0. And see what we can do. We can factor out at least a 9, I think even more. Yeah, I think we can factor out an 18. 18x in fact, maybe? That sounds right. Yeah, okay, so maybe I'll get 2 x's left, and minus 1 equals 0. So then the point is, you know, this is, I think, as factored as possible. When you set 18x equal to 0, you get x equals 0. When you set 2x minus 1 equals 0, you get x is equal to a half. So I believe those are the two critical numbers of f. And so for local min max, I mean, we can go about doing this, like f prime. Ooh, here's the issue. So we do include the x value 0. We include the x value 1/2. But I think it's actually going to be really a lot of work, to be honest, to check does f prime change from positive to negative or negative to positive around 0 and around 1/2, because we have to pick an x value like before. So I'll say for this problem, strategically, look, we want these critical numbers of f, but probably we don't want to use the first derivative test because the numbers are, you know, you have to pick like 1/4. I'm sure it could be done, but it might actually just be more succinct for us in this problem to look at the second derivative. So from f prime, f double prime of x is 72x minus 18. And then if we compute f double prime of the two critical numbers, so f double prime of 0, plug in 0 there, you get negative 18. So what does it mean that the second derivative is negative? We've got concave down, this kind of shape, right? So concave down means that there's right where the slope is 0, the slope we set equal to 0, right where the slope is 0, right at the top. Oops, I should just do that. Right there, there's got to be a local max. So f has a local max at this x value of 0. What about f double prime of the other x value 1/2? So f double prime of 1/2. So go back up here. There's our f double prime of x, plug in 1/2. 72 times 1/2 minus 18. So what is this, like 36, I guess, minus 18? Okay, so that's positive. So we have a concave up. If we were to draw f, we'd see concave up right at the x value 1/2. So we'll have f has local min at the x value 1/2. Okay, so both of these are by the second derivative test. Let's take a look at exercise 4, which at least uses the same function, so we don't have to, maybe, you know, we can kind of save on some of our work here. Exercise 4 is now the absolute mins and maxes of f of x, same function, except now an interval has been given. What is that interval here? Negative 1 to 1. So how's this work? Well, what we have to do is take these, it's a lot of the same work, right? So we take these x values, and we need the actual y value, right? So we need the y value for this function at x is 0, at x is 1/2. Often people want to take these numbers and plug them into f prime. But you will know, because we set f prime equal to 0 and found these x values, if you take these x values and put them in here, we're going to get 0. F prime of 0 is 0, f prime of 1/2 is 0. That's for sure, right? Like that's not what the question's asking. Absolute min and max is like where is the biggest y value? Where is the smallest y value? So we need y values. So we should compute f of 0. We should compute f of 1/2. But we should also compute f at the endpoints. This is just the method that's used to find the absolute min max of a continuous function. So the endpoints is what? F of -1 and f of 1. So f of 0, okay, again, f is right here, right? So plug in 0 to x everywhere, you're going to get 0 minus 0. Plug in a half, that's going to be a little bit of work, isn't it? So let's see, 12, I was not prepared. 1 half cubed minus 9 times 1 half squared. Okay, well, let's work out some of these details. So this is an 8 in the denominator. 12 over 8. 12 over 8. We can cancel out 2 on top of this. So 6 over 4. Cancel more. 6 over 4. 3 over 2. 3 over 2 for the first term. And then this is a 9 over 4. Actually, here's what I'm going to do. Sorry to call on audible. Let's, instead of 3 over 2, let's write this as a 6 over 4 still. So we won't cancel all the way, because at least we have common denominator. We get here negative 3 over 4. I hope the arithmetic is all correct. At least the principle is. F of negative 1, plug in negative 1 everywhere. So 12 times negative 1 cubed. Negative 1 cubed is negative 1. So negative 12 minus 9 times, well, negative 1 squared is a positive 1. So we end up with here 9, 11, negative 21. F of 1, plug in 1 for x here and here. So we have 12 minus 9, which is equal to 3. Right? So let's see, let's compare these numbers. Are these easily comparable? I think they're not too bad. The smallest number is here. So this is the absolute mean. Right? That small, the negative, this negative number totally beats that negative number. And then the positive, 3. Yeah, so these are absolute max. Okay, so notice there are some similarities. I think the key thing to keep track of is for absolute min max, you are ultimately in the end looking for the y value. It's just where the critical numbers are. Like typically where the slope is 0, that's a good place to look, where you might have a hill or a valley. That could be a candidate for the largest y or the smallest y. But you have to check the endpoints too, because the endpoints are like places where the largest y or the smallest y